A warm welcome to the all audience. Welcome to the International Training and Internship Program on opportunities for R&D ecosystem and tech-driven startups. The program we started on 20th of June and will be going on till 15th of July. This is Mukesh from Tech Counselor team, and I welcome you on behalf of Tulas Institute Dehradun as well as the Tech Counselor team as an organizer. I'm very much thankful to my co-organizer, Krishna Institute of Medical Science, deemed to be University from Maharashtra, as well as to my technical sponsors, Uttarakhand Technical University and TQ. Also, we are very much thankful to the knowledge partner and technical partner, which include Ramanujan Academy of Science and Technology, Yuvayana Tech and Craft, Swachh Neer, Boudik Ventures Private Limited, Kaviraj Foundation, and Triads. So this program we are organizing under our initiative, a virtual network of Indians, AVNI, in short. And I'm very much thankful for the organizer and to the whole class team for initiating such a wonderful program, which is totally focused for to boost the R&D ecosystem and to have that kind of ecosystem in the India where tech-driven startups can actually boom and all. So Tulas have this business incubation center as well as at the campus, and certainly I believe the whole motive was to boost the startup and entrepreneurship kind of thing culture in the with the students and everyone. So for that, if anybody want to have any kind of support, they can always contact the last team as well as to the tech counselor team. Our technical partners will be supporting all the student and faculties for the mentorship as well as with the IP and all. For example, Boudik Ventures will be supporting with the trademark filing to 5 of the startups. And for IP health check, they'll be having free consultancy to 10 startups. So these are our organizers and co-organizers. So for the whole month, we will be having around 10 plus experts for you can say 10 plus module who will be taking lectures for 40 plus hours and extensively focus on research, development, and innovation. So in line with the government goal to aim, like our aim should be to make India a global R&D hub. We have planned this particular session and this particular event. So this was this came as an idea to organize such an internship post COVID, where like a student were having problem with their internship and training. So we came up with this idea, and Dr. Sunil Samwal as a secretary for the event, and Mr. Divakar Pant, they have come up with the whole idea in collaboration with the tech counselor team. So we will be having Dr. Fabio Massi. We had Mr. Madan Kanala, Dr. Raman Sharma yesterday, who is the senior scientist at CSI at Delhi. We also had Dr. Rajkumar Helder, who is the CEO and founder for Rivenal Biomedical OPC Private Limited. And he took a very wonderful lecture on research and development and research and innovation on biomedical and defense sector. We also had very senior professor Dr. Manoj Kumar Panda, who took a very wonderful lecture on like the solar and renewable opportunities in the startup domain. So other than that, we had Mr. Vinay Chaudhary, who took the lecture on IoT on very first day. And then we had Mr. Saurav Trivedi, who is the founder and director for Boudik Ventures Private Limited with us. And he took a very wonderful lecture on IP. So these people already have taken the lecture, and in coming days we will have Dr. Fabio Massi, who is the technical director and R&D manager for the IRI-DRA at Italy. We will also have Dr. Amit Kumar Mondal, who is the assistant professor at Dubai. Then we will have Mr. Naveen Kumar, research engineer at Studio de Research at France. Siva Prasad Koyadas will also join us in the coming days. And then we will also have very senior professor Dr. Sunil Samwal, who is the HOD and professor at Electrical Engineering Department, Tulas Institute of Dehradun. Mr. Ajit Kumar Yadav, the researcher at NISA project, a joint initiative between NASA and ISRO, will also be joining us. He is the founder for Ramanujan Academy of Science and Technology. From Tech Counselor team, Uday V. Mittal will be taking lecture on applications for the Arduino and hardware on the tech driven kind of thing. Then Ms. Sakshi Gupta, assistant professor at Gafigara University, will also be taking a lecture. Additionally, we will have Dr. Jayant Pamar and Yasodhan sir, who will be taking lectures on agri-tech as well as on the domain for more like current scenarios. Then the concluding remark will be given by Ms. Renu Thaplial. She is the co-founder and director for the Tech Counselor team as well as the founding member for the Kaviraj Foundation. Today we have Abhishek Gupta sir with us, and he'll I hope that his vast experience on the domain will be very helpful to our audience. So these are like among our speakers who took lecture. Like for the Vinay sir took on the IoT and embedded in today's startup and tech-driven R&D ecosystem scenarios. Then we had Rajkumar sir, Madan Kanala, then Saurav Trivedi, Manoj Kumar Panda sir. Then yesterday we had Dr. Raman Sarma, a very wonderful lecture on grey water and its application for the coming days. So before I hand over session to Mr. Diwakar Pant, I heartily thank you to all my organizers, co-organizers, and to my whole team for initiating such a wonderful session, and especially to Tulas team for providing this platform to everyone. So I request Mr. Diwakar Pant sir to kindly introduce Mr. Abhishek sir for the session. Handing over session to you, Diwakar sir.
Thank you, Mr. Keswalji. First of all, a very special good afternoon to all the participants present over here. I also like to welcome Mr. Abhishek Kumar Gupta. I would like to read the brief profile of Abhishek sir. Abhishek Kumar Gupta received the Bachelor of Technology degree in Electronics and Communication Engineering from the Galgodia's College of Engineering and Technology, Noida, in the year 2008, and the Master of Engineering degree in Electronics and Communication Engineering from the National Institute of Technical Teachers Training and Research, Chandigarh, India, in the year 2013. He was a senior research fellow with the physics department.
Diwakar sir, I think we lost your connection.
And a junior research fellow with the Tata Institute of Fundamental Research, Mumbai, India, during the year 2016 and 18. He is currently a researcher with Extreme Light Infrastructure, a non-profit organization, Szeged, Hungary, and his research interests include terahertz antenna design, terahertz time domain spectroscopy, and ultra-fast carrier dynamics in semiconductor materials. So today he will be giving a lecture on the road to the terahertz technology. So I would like to welcome Mr. Abhishek Kumar Gupta. So please, sir, welcome to you.
Thank you, Mr. Devakar Pant. Thank you very much for a warm welcome. I hope you guys can see my screen. I've shared my presentation. Please just confirm this.
Yes sir. Yes sir. We are good
Yes,
to go
sir.
with your screen.
Okay. So, welcome everyone. Basically, my name is Abhishek Gupta, and I'm working as a researcher in ELI-HU Szeged, Hungary. And my domain is basically in terahertz technology, and we do various kinds of experiments in lasers all over the electromagnetic spectrum. And in my lab, basically, I'm working on this time domain spectroscopy of terahertz, which has many applications. And today in the presentation, I'll be basically uh, talking and sharing about the basics of terahertz and what are the applications of terahertz in the industry and in the various other sectors. So basically, as you can see on my first screen, the title which says the road to terahertz technology. Terahertz is basically so the plan of talk basically is what is terahertz, because I assume that I have a vast range of basically people who will be listening to and attending this presentations. So I have kept my presentation very basic so that it will be very easy to understand for everyone. So the plan of talk goes like what is terahertz, a history of terahertz science, what is something which makes terahertz unique, applications of terahertz in various sectors. There are few shortcomings of terahertz too, and then finally I will conclude my presentation. So what is terahertz? As you guys basically know about radio waves, microwaves, X-rays, ultraviolet rays, and the thing is that in the electromagnetic spectrum we have different frequencies which have different applications, and mostly people know more about radio waves, microwaves, and X-rays because they have seen and they saw these applications in the day-to-day life. But there is a spectrum in the electromagnetic electromagnetic spectrum, there is a certain range of frequencies which comes between the microwaves and in the visible range, which is called terahertz frequencies, which actually are not explored much throughout the time because of the certain problems. But the thing is that the terahertz frequencies have lots of potential and applications which are currently being explored and going on like explored in the time. So 1 terahertz is basically 10 raised to the power 12 hertz. The frequency range of the terahertz frequencies comes like between zero point 0.1 to 10 terahertz. The wavelength range is like 3 millimeter to 30 micron. That is why these terahertz frequencies or terahertz waves are also known as sub-millimeter uh, waves. The equivalent temperature, according to these terahertz radiation, is something like between 1 to 100 Kelvin. And the photon energy, which is a very important point of these terahertz radiations, is that the photon energy range comes from 410 microelectron volt to 41 milli electron volt. And this is a very important aspect as compared as I mean in terms of the applications of terahertz, because of the low photon energy of terahertz. There are many applications which I will be sharing in the coming slides. So if you go to the history of terahertz science, how this terahertz word come into the scene. 1 terahertz is basically 1 million times per second, and the word tera basically comes from a Greek term meaning marvel or monster, which in a sense like that is a huge and marvelous quantity. That is why we say terahertz is like 10 to the power 12 hertz, because it's a very high frequency range. Now the next important question which comes into the picture is what makes terahertz unique. Why we are like so talking about terahertz frequencies nowadays? Due to low photon energies, they cannot lead to photoionization in biological tissues as can X-rays. As a result, terahertz waves are considered safe for both the samples and the operator. As discussed in the previous slides, where I emphasized more on the photon energy of terahertz, which was between microelectron volt to millielectron volt, because of the low photon energies, they cannot lead to photoionization in biological tissues. When I say photoionization, basically photoionization is a physical process in which an ion is formed from the interaction of photon with an atom or molecule. So, because of the low photon energies of the terahertz, they will not lead to the ionization of the in the biological tissues, as basically which results in X-rays. Because in X-rays, the photon energies are very high in electron volts, so they can harm the biological tissues. But in case of terahertz, because of their low photon energies, they are considered very safe for both the samples and the operator. Another point is that terahertz waves cannot penetrate into the human body just like microwave can. Therefore, even if terahertz waves do not cause any harm, it is limited to skin level, which is very important, because I will be sharing many applications in the coming slides where why is it important to have the terahertz waves up to the skin level. They should not penetrate, because they cannot penetrate into the human body on the skin level. On the top layer of the skin they can only gives you the results in the spectroscopy. Therefore, they do not cause any harm as compared to the other frequency range like microwave and X-rays. Another important point is that terahertz waves are transparent to most dry dielectric materials such as clothes, paper, wood, and plastic. That is why terahertz waves are considered very promising in non-constructive evolution applications. This is another very important point, that because the terahertz waves are transparent to basically clothes, paper, wood, and plastic. So if you want to do certain experiments, or if you want to have certain applications where you don't want to basically damage your samples, then these waves are considered very promising. When I say this deconstructive evolution, I mean basically NDT is a wide group of techniques used in science and technology industry to evaluate the properties of a material, component, or system without causing damage. So the promising point is they will not create any damage to your samples, whether it's a paper, wood, or plastic. So it's useful in these aspects. Another important application or thing about terahertz is that the unique rotational, vibrational, and translation responses of materials, for example, like molecules, radicals, and ions, within the terahertz range, provide information that is generally absent in optical, X-rays, and NMR images. This is another important point that there are certain materials, there are certain molecules or ions which have like unique rotational motions, vibrational motions, and translation motions. So if you want to capture the responses because of these different vibration or rotation responses, you can extract many different properties of the materials. For example, in case of molecules, or for example, in case of water, H2O molecule. So the required information which you can get from terahertz is generally absent in the optical regime or the X-rays or NMR images. Basically, NMR stands for nuclear magnetic resonance, and it's an analytical chemistry technique used in quality control and research. So again, the importance or what it makes terahertz unique is that you can extract information of molecules from the terahertz. So these transitions basically are specific to the molecule. I mean, it depends upon different molecules. So different molecules will have different transitions, and they will give you some specific signatures into the terahertz frequency range, and therefore it can enable spectroscopic fingerprinting in the terahertz range. So this is another point which makes terahertz unique. Characteristic properties of terahertz radiations are high penetrating depth and low scattering combined with good spatial resolution. This point is again very important when I say good spatial resolution, because the resolution of terahertz wave is something like around 1 millimeter. So what happens is that if you have a good resolution of terahertz frequencies, while in the transmission of certain samples, uh, you can get a good quality imaging of whatever sample you're talking about. Apart from that, basically uh, coherent terahertz signals can be detected by mapping the transient electric field in amplitude and phase, which gives you the access to the absorption and dispersion spectroscopy. So basically, this point is mainly important in terms of terahertz spectroscopy techniques, where you can detect the field, the amplitude of the field and the phase, which can give you more data from these signals. Now move on to now in the previous slide we already now know that why terahertz is so unique as compared to the other frequency ranges in the electromagnetic spectrum. So what are the now the different applications of terahertz? You can see terahertz has like different applications in security, in pharmaceuticals, in terahertz food inspection, ceramic industry, automotive industry, medical diagnostics, terahertz imaging for sciences and communication. I will be basically explaining you all the applications in detail, one by one. So if we go to the first application, which is the security application, what happens is basically that terahertz waves are completely harmless for human and have no ionizing radiation as opposed to X-ray machines, but can easily penetrate clothes, garments, and other enclosures. Such properties makes the terahertz-based people screening solution extremely valuable for applications where human health and safety are of utmost importance. So it's a quite interesting slide and picture which you can see on the screen, that basically says that is X-ray privacy concern. I mean, now basically in this slide and the next slide, I will be just giving you a clue that why X-rays are not good, why they are harmful, and in most of the airports, basically you see scanners which are like X-ray scanners are installed, which may harm the which may harm your body or maybe certain privacy, and any many things are actually concerned in the X-rays. So which is not considered a very good method to have a X-ray check on the airport scanners. You can see a cartoon where like they're mocking about basically about the X-ray screening in the security. Like the question then goes similarly, like is it not harmful, the X-rays? Basically definitely yes, because of the photon energy, high photon energy of X-rays, they are considered to be somewhere harmful as compared to terahertz. So then the question comes, that is the importance of application of terahertz is in securities. So it is used for airport security. Terahertz is used for airport security to detect illegal substances hidden in public flows. This would be a great alternative to the X-ray scanners. That is why I showed you the previous slides where you can see the X-ray scanners, which can basically harm the human body or tissues, biological tissues. So this terahertz frequency or terahertz radiation can be basically would be a great alternative to the X-ray scanners. And some airports have already started using the as a terahertz waves as are much lower in energy. Even in Europe, basically, I've seen like many airports have installed terahertz scanners, and you usually just walk away to the lane, and basically it's not that you have to stand like in the X-ray machines or something like that. You can see in the pictures also, in the first picture on my on the right topmost right of the PPT, where a guy is having a knife which is like hidden by a newspaper. But if you have like terahertz frequency or terahertz scanners, you can easily detect that he or she is carrying a knife. Similarly, for example, if somebody has these dummy, basically explosives belt tied onto the waist. This can also be detected by terahertz frequencies because the of because of the application of terahertz, basically, which I shared in the previous slide, that it can pass through the it can basically it reflects the metals. It can pass through papers and other objects, so you can easily distinguish that if somebody is having some some destructive materials in onto their body and the pocket or something like that. In the lower images, in the lower bottom also, you can see the images is on the right lower side of the screen. Basically, if somebody is carrying a gun, so it's not like you have to like scan them onto using a X-ray machine or something. If this guy is passing by through the lane, you can easily detect. So the important point is in terms of security, that you can detect these kinds of things even if the object is very far or the person is very far, up to like 1 meter or 2 meter. It's not that you have to be closely scanned into the limit. So you can see basically the cold steel, firearms, bomb and hand grenade, and many many of these things can be checked on the airports. And basically, how it works is that it operates in the reflective mode, in the reflective mode of terahertz, and basically is intended to stand off detection of weapons, including cold steel, firebombs, grenade, and many things which are hidden under the clothes of the people. So this is also one of the important aspect and application of the terahertz frequencies. Now you can see another application in the security only is the security screening of letters, envelopes, and small packages. As you can see on the again on the image, the top image where you can see the terahertz image of CD in an envelope. Then you can see a terahertz image of a handgun in a box, and many other objects which are hidden inside, in the object. It's not that if they have like hidden inside some boxes, which can be like wood boxes or it can be envelope, for example, we can still figure out and tell what it is by using the terahertz radiation. So, and apart from the one which I showed in the previous slides where the people were carrying gun or something, there are terror methods which are becoming more ingenious and now include letter bombs that can injure or kill not only the recipient but also mailroom and delivery staff. For example, in that case, they don't have to have a person which is directly creating chaos in the security or on the airports. They can just put some kind of letter bombs or some kind of powders which are harmful into the envelope, and it can basically kill or affect many people at a time without using the resources. So with the
Abhishek sir, sorry to interrupt you, sir.
yeah.
Actually, the voice is quite low. Can you like enhance the voice or mic position and all?
Okay. Okay, so now is
Yeah,
it fine? Is it better? Can you hear me?
yeah, it's good. It's good, sir.
Okay, so sorry for that. So basically, yeah, I was talking about that. Basically, if you detecting powder, liquids, explosive, and other threats in small packages and in mail is recently acquiring high importance. So now there are different kinds of things which are used for an attack or for killing people. Like these are the different kinds of methods. So after discovering letters containing anthrax, anthrax is basically is like infectious acute illness with in some form with a higher mortality rate. It is basically most common in wild and domesticated ruminants, but when it comes in contact with a sick animal, it, 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 its tissue can also infect humans. So basically, if you have like certain letters which you receive from someone which is containing this anthrax and other threats like chemical, biological, and radiological elements, this can be perceived by using the terahertz radiation in real, and you can have a effective methods to approach them and counter them. So just like I told you in the previous slides that these are the for the security application, these are the methods where people were directly carrying the weapons, and these are the methods where the weapons were not like it's like a biological weapons or chemical weapons which can also be used. So terrors also have like applications which to detect these kinds of biological weapons or chemical weapons. Now, if we move towards another application of terahertz in pharmaceutical applications, so pharmaceutical industry is supposed to heal and cure, and so it simply cannot afford using X-ray technology that emits ionizing radiation, which is knowingly detrimental to human and animal health. So in this contrast, basically, terahertz rays and terahertz imaging are unique and have the safe alternatives. Many materials used in the pharmaceutical cosmetic industries are fairly transparent in the terahertz spectrum. This makes our technology, the technology very attractive as a harmless and non-destructive testing technique used in the production of drugs, medical products, and diapers, many applications. So if you can see in the slide, basically that if you want to have a quality control in pill production, that you want to see whether the box of the tablets which you have buy from the stores, or is like maybe can have a couple of tablets less or something. So it can be because of the human error, because like due to the human error, imperfections in existing production lines and other factors, mainly like pharmacy related manufacturers, badly need to like make sure that every pouch in the tablet blister pack is properly filled, and there are no empty blisters, at the end of the process line. Likewise, it is important to also check if quick dissolving capsules which have been properly filled with the active substance. So another task is to check plastic pills container for fullness, because basically plastic containers are intentionally kept or manufactured opaque, invisible, right? So that they should not damage, or damage the pills or something. So basically they are kept opaque in visible light, while they are remain perfectly transparent in the terahertz spectrum, and can be subjected to the non-destructive test inspection basically. So in this slide, what I'm trying to emphasize the point is that if you want to have a quality control in pill production, and because of the problems in the x-rays, you want to have like some kind of scanning where you can see whether whatever things you have packed in terms of like pills and other medicines, the quality is good, and whatever coming out is like full. There's like no human error or tendencies. So again, terahertz can also be used to check this quality control. Another application is like, for example, you can see this image of the diaper. It's also again very important, because to determine the presence of the moisture, foreign bodies, or other contaminants, you need to do some kind of testing, which should also not destroy these kind of materials, but also give you all the properties, or the thing whether the mass production of all those things will not create any problem. So in quality control in the diaper production, and this is an important application associated with the non-contact, non-invasive, non-destructive testing and quality control in the production environment. These things can also be taken care by the terahertz radiation. Apart from that, the quality control of in-stock items. For example, you have like cold storages and various storages where you stored tons of pharmaceuticals and cosmetic products for months at various warehouses before they finally reach to the customer. So it is very important when they reach to the customer, it should be like the same. What should not be get degraded by the time, because it's stored for months in the warehouses. So depending on the storage condition, the packaged item can be affected during that period, but it is difficult to tell what exactly is happening inside the package. So again, terahertz has its applications. I'm again repeatedly saying that you can also test these things and have a quality control check of these stock items also. Okay, moving on to the another application, which is like terahertz food inspection. So this is again an important application in terms of food, that it is critical for the quality control, and uh, so basically it's very extremely useful in the terahertz imaging in the food industry. So instead of like again I'm repeating this thing, that instead of using X-ray machine, food manufacturers and packagers can also use these terahertz food scanners, for instance, to check if pick and place, the robotic arm for all the candies bar, or from other or for other items. For example, again, you can see in the presentation that okay, the image is not quite very good, but you can see basically you can see, if you can see my the cursor, I'm pointing toward the cursor, that they are using they're basically imaging these candies or the chocolates, and you can see at the end of these one chocolate bar is missing. So basically, instead of using the X-ray machines, you can use a terahertz scanner, and you can see if something is missing into the packaging or thing. So you can easily see in the food scanners, this one chocolate bar is missing. Another, you can see a noodle pack with the seasoning sachet, where you can see the missing sachet. So basically, in this case also, in the previous thing I was talking about. I was talking about the other things. So here, as in food, items also, you can easily see whether something is missing or not. And you can also, basically it will also not affect the food quality also, which is also very important. So you can have a scan of various food items, and it will not basically destruct or degrade the proportion of whatever ingredients they have. And you can also easily detect whether something is missing or not. Apart from that, again, you can see it's in the food safety also. For example, like if you have some food item, you open it and you find find an insect or something, which are like packed items. So basically, it's also very harmful. So if you have certain packaged food items where you can have a quick terahertz scanner, password quick terahertz scanner, you can easily see if you find some insects or foreign objects inside the food, which can actually create serious cause of concern for the consumers, food manufacturers, and retailers. So basically, if you have certain kind of technology, or if you have some kind of scanner which you can easily scan all the food items, it will be good, because it also degrade the name of the manufacturers or the retailers. That if you find certain high brands and something which you see, okay, you buy something from that brand, and then you figure it out, okay, this is some insect into that material or food item, you will not maybe buy that for the next time. So you will avoid that particular brand or something. So for the manufacturers and for the retailers, this is a major issue of concern, where you can basically check any kind of foreign objects into the food, which can be easily checked by the terror scanners. So again, what it is written here, that unwrapping a chocolate bar might reveal an unpleasant surprise, such as insect, pieces of metals, or glass, or clothes, or dirt. So you can see that I'm emphasizing again on the applications of terahertz scanning or imaging in all the the day to day things which we are using in terms of food, in terms of like many things. So again, I'm showing this picture where you can see basically a polythene bag, which is something like 2 centimeter thick. And then on the besides, you can see an image where they have shown that while imaging this polythene bag, you can see a housefly under this polythene bag. So the point is, even if the polythene bag in which the fly was there was 2 centimeter thick, the terahertz scanner or the terahertz radiation can penetrate through this polythene bag, and you can basically figure it out whether it has some kind of foreign material. And in the color bar also, like how you can see in the color bar also that uh, because of that housefly, the transmission from that point is basically low. So so okay. Yeah. So this is also again in terms of the food safety. Another image you can see, where you can see a metal screw on a chocolate bar, and then you can see a terahertz image of that metal screw. So basically, other parts of the chocolates have different kinds of a color spectrum as compared to one where you see a metal screw. And test terahertz basically gets reflected by the metal, so you can see a change in the spectrum. And then the other two images on the bottom, where you can see a metal stick in the flower, which gives you a different kind of imaging, definitely. And then you can see in the last image, you can see the upper nut, which is basically infected by a fungus. So in this case also, if you have certain things which got infected by some fungus or other kind of thing, so in while doing the imaging, you can easily distinguish that, okay, this thing is fine, and this thing goes bad, without even opening the package. It's also very important. So these are the applications in the food security. Then again, there is one more image. You can see the terahertz imaging of seeds. So sunflower seeds, basically terahertz imaging, and you can see, because you can see something like 9 seeds there, and if you want to figure it out that some seeds have gone bad, how you will be able to figure it out without opening it, or without checking it literally. So if you can have an image of the terahertz, you can see that the sunflower seeds with the increased acidity level have much lower terahertz transmission. So and at certain points, or certain in the image and the graph, you can see that the color code or the transmission is very less as compared to the other parts of the image. So this also you can figure it out. Okay, so just I'll take a 1 second pause before moving to the applications of terahertz in ceramic industry. So continuously, I'm talking about all the applications of terahertz industry, and we are basically somewhere around uh, halfway path of the applications of terahertz. So still, you can see that so many applications of terahertz range, or terahertz frequencies, or terahertz radiation is there in all the aspects of day-to-day life, or the things which we are used. So moving on to the ceramic industry. So again, you can see the terahertz transmission image of a green ceramic tile with strong moisture gradient, like up to 3%. So if you see this green ceramic tile on the left hand side, by just seeing, you cannot figure it out about if there is something wrong with this tile. But if you do the terahertz imaging of this tile, you can easily see in the image of the right hand side the color contrast, because the transmission throughout this green ceramic tile is different. And why it is different? Because the moisture gradient of this tile actually is varying, from point to point. So basically, everybody is using these tiles, for the construction purposes and everything. So this can also be figured it out. So what it says that one of the most notable applications of the terahertz system is an evaluation of density and humidity variations in pressed powders, basically. So one of the important aspects in the ceramic tile industry is to monitor density gradients in green tiles right after they're being formed in a press and examine finished tile for various defects. So even after the manufacturing and everything of these tile, if they have certain defects, these kind of defects can be figured it out by using the terahertz radiation. If you pass terahertz waves through that, you can easily differentiate or figure it out whether the tiles which are manufactured at the end is right or not, in terms of many other uh, 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 properties. So unlike X-ray technology, basically terahertz imaging is highly sensitive to density deviations, and especially to moisture content of the ceramic samples. It can be used to monitor density deviations in a tile right from the forming press, and to provide feedback for a powder feeding machine. So basically, in the lower image of C, you can see in this tile there is a crack in the corner, which can easily be seen in the terahertz imaging. This crack. So the hidden defects. So basically, if you have this terahertz, if you have this tile and you wrapped it into some kind of container, and you don't know whether this tile might have like broken or have some crack kind of thing. And when you open it, when you buy it, you open it, you see, oh, it's already cracked. So for while the manufacturing, or at the end of manufacturing, if you do all these kinds of you know check the terahertz transmission from these certain tiles, you can easily see if this is having certain defects, or there is any change in the density or the humidity while manufacturing. One more picture, which is basically showing the image of a dry ceramic tile, where you can see the holes and scratches also. And again, you can see basically in the lower picture, you can see different tiles with different thicknesses, and according to that, you can see the different transmission of the tiles. Okay, moving on to another application. So we have this destructive testing inspection for wood processing also, where you can find the hidden defects in a wood. So basically, again, I'll say this that anything which I'm taking, anything which I'm putting under the Terahertz scanners on the Terahertz system, basically have application. So whether you use a metal, whether you have a like metal thing, whether you have some wood, whether you have a paper, so all things basically you can figure it out. So this gives you the strength and the potential of the terahertz, which basically can be applied to anything. So it's like mostly have application in all the areas. So in this slide you can see basically on the right hand side where you can see a knot, in a defect in the wood, which is basically very difficult to detect otherwise. But when you do this imaging of these words from the terror scanners, you can figure it out in the spectrum. So you can see basically if it's a metal screw, you will have different kind of transmission through that metal, or if you have a knot, you have different kind of transmission, or basically it will be low in transmission. So you can figure it out. Okay, this particular thing have some problem. So also there are lower images which you can see. And in the lowest one, you can see if you can also figure it out whether the wood is basically dry or wet, because terahertz actually get absorbed by the water. So if you have wood which is a bit wet, so basically the transmission from that would be lower. So this also you can figure it out at how much moisture content is there in the wood, or is it gone bad or something. So all these defects, like which includes, are only not limited to the knots, hollows, and foreign bodies like nails, screw, wormholes, like and as well as wet areas. So some basically rods don't produce color contrast, but the birefringence of rod is much lower than the wood around it. So which allows detection in the Telluride spectrum. Apart from that, other promising application includes detecting termites and other insects inside the wood and analyzing the wood for moisture content. You can see through the terahertz frequencies. Okay, moving on to the next slide. Now we have one more application in the automotive industry, and I'll just gonna tell you in a second that what and how terahertz can be used in the automotive industry. Okay. So you see the slide. Basically, uh, research into new materials and into the semiconductor technology has expanded the existing boundaries of terahertz technology, opening the doors for its commercializing in numerous markets and applications, including the automotive industry. So, how terahertz has their application in automotive industry, we can see, and also you can see the images, and maybe now you can like able to figure it out by seeing the images also, that like many tire manufacturers require a harmless, safe, and effective solution for inspecting steel cords embedded inside the rubber tire. So this crucial task is to check the embedded metal wires for continuity and for the availability. So car tires are made of like 1 to 2 millimeter thick rubber pads that are pressed together in a sandwiched manner to form a robust tire layer. So so steel cords to be inspected are usually something like around millimeter in diameter, which lies perfectly within the range of these terrar scanner. So in the images, you can see whether when the cord is so the thickness of this uh, kind of coating or outer coating is 1.6 millimeter, and the cord is removed. So if you want to figure it out, that whether the cord is there or not, you can do the terahertz imaging, and then you can easily see where the cord is removed. You don't see any kind of basically it's like 100% transmission at that point, because there is nothing at this point. Apart from that, if you want to Like if you have some metal stencils of the various types of marks or imprints you want to make on your tires or something. So you it's very important because you have to figure it out about the dimensions, that whatever stencils you have made after the production, whether the sizes or the dimensions of these metal stencils or anything is like the same or not. So this also you can basically have a terahertz in imaging of that, and you can easily see whether while the manufacturing of these kinds of things, whether something got bad during the manufacturing, and you can easily basically figure it out in the final makeup of this metal. It's just another important part is that about the corrosion in the automobile parts. So most metal automotive parts are exposed to corrosion, but it is often very difficult to determine corrosion due to the fact that because these parts are coated with paints, uh, for example, in like body parts. In other cases, the steel reinforcement of rubber belts or tire is subjected to corrosion, and you have to like figure out this corrosion also, that how much it is like corroded. So non-corroded metal parts will clearly reflect the terahertz signal, because as I told you earlier also, that terahertz radiations or waves are reflected by metals. So if the part is not corroded much, basically you will get all the terahertz reflected, and you will see different kind of a spectrum or transmission in the imaging. But you have some corroded parts where basically the terahertz can pass through, because that metal part or the automotive part got corroded. You can easily figure it out and distinguish in the images that where basically you have the part of the metal which is corroded, or the automotive part. So you can see basically in the first image, this is a terahertz reflection image of a metal part with bad corrosion, and you can easily see in the spectrum of this one, and the other with like without corrosion, and you can see the difference. So basically, if with more corroded, it's just the transmission will be like higher, but if it is like less corroded, the transmission will be lesser. So for checking off these automotive part or automobile parts, you can easily figure it out. So it has like this application is also very important in the automotive industry. Now one of the important, and I'll say extremely important application of terahertz is in medical diagnostics, because I think life is above everything. So 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 terahertz. So I'll go again with a brief, with a kind of a technical thing detail about the terahertz, which I told you in the initial slides, that terahertz photons are basically not sufficiently energetic to break chemical bonds or ionized molecules or atoms, and therefore harmless for living organisms, as opposed to high energy photons in X-rays or UV rays. This thing actually I mentioned earlier also, that X-rays and UV rays have higher energies and higher energy photons as compared to the terahertz photons. So terahertz radiation is not like highly scattered in tissues, unlike in optical transmission. And besides, due to the strong absorption of terahertz rays by water, terahertz imaging can be very useful tool to investigate soft tissues. So these unique properties of terahertz makes them eligible for use in various medical applications, uh, some of which hold enormous promise for certain aspects of diagnostic or described. I mean, it's kind of diagnostics. So you can see in the slides where on the, maybe I'll start with the left part of the slide, where you can see cancer image just under the skin of a human tooth. So basically, Terahertz radiation, as I told you, can also detect differences in water content and density of tissues. Such methods could allow effective detection of epithelial cancer with a safer and less invasive or painful system using imaging. Because you see that okay, if a person has some problem with his or her teeth tooth, and so if without going or digging into the mouth, basically, if you have certain methods which you can where you can like invade that what's the problem, so terahertz frequencies can be used, and some like frequencies of terahertz radiation can be used for the 3D imaging of the teeth, and maybe more accurate and safer than conventional x-ray imaging in dentistry. So below you can see the transmission of a human tooth. This pink part basically in the center shows location of the buried decay, so like the part which is affected, and how it can be distinguished by having this terahertz imaging is that because terahertz waves got absorbed by the water, so the density or the water content in the tissue will change if it is damaged. So when you get the spectrum of the terahertz imaging from that teeth, you can easily see the difference in the image, because where you can see the red patches, because here the water content has gone lower and the density of tissue is also lower. The terahertz can pass easily, and that's why you can see the high transmission as compared to the other part which is healthy. So if certain person develop these kind of cancer, or in the initial stages of to detect the cancer, basically like stage 1 or something, if you have certain terahertz imaging, you can figure it out in the much earlier stage. In the right hand side, this is an image of mouse prostate section with tumor tissues, as imaged with terahertz, optical and staining techniques. So the terahertz image above shows a significant reduced absorption of terahertz radiation in the region compared to the normal tissues, suggesting it's useful for detecting tumors. So here you can see in the image where you have a terahertz image of a prostate section of the mouse, where you can see the difference where you have the stain, and this is the optical image of that, and here this is the terahertz wave. In the terahertz image, you can easily distinguish basically that how much transmission is going through, and you can figure it out where's the problem in the tissue, or where is the tumor basically. Okay, moving to the next slide. Now again we have another application is like the non-invasive techniques for early detection of cancer, as I gave you a glimpse about the same in the previous slide, that you can see this tumor tissue, like which is you can see it's very bad, but so you can have a terahertz imaging of that, and you can uh, easily detect where is the problem part, or where is the tissue which is damaged. So the important part here is basically you can see, because all these things are related to the human body, where the parts are so sensitive that you don't want to damage the good cells, and also you want to detect the cells or tissues which have tumors. So basically here terahertz frequencies or terahertz radiation have like very important role which plays to figure it out and detect the cancer in the early stages. So as you can read also, like the most recent achievements in the terahertz in the field of medical imaging have dramatically enhanced early detection and treatment of many pathological conditions. uh, Terahertz imaging system can help in detecting early cancer before it's visible or sensitive to any other identification means. So this surely this line gives you the edge of the terahertz frequencies over other frequencies, because you can like detect it before it is visible or sensitive to any other identification means. I mean, it's like really visible what's happening. So the latest Research aimed at examining terahertz properties on skin cancer, breast and colon cancer tissues discovered that refractive index and the absorption coefficient of the tumor tissue was higher and in comparison to the normal tissue. So basically, you have the terahertz radiation which you pass through, or have a scanning of these tissues, and then you evaluate the amount of absorption which has happened in the tissues, and then you can easily see the difference in the tumor tissue, sorry, and the normal tissue, because the tumor tissue, there will be like the absorption coefficient will be higher as compared to the normal one. So these such distinction is possible due to the higher water content, because I told you and again tell you that terahertz radiations get absorbed by water, definitely. So if you have like if the tissue or something has a higher water content, for example, in like different kind of cancers, for example, breast cancers and other skin cancers, and so you can easily figure it out the differences because of the higher water content and the structural changes that occur in carcinoma, which is like increased cell and protein density observed in cells affected by the diseases. So terahertz pulse imaging technique is highly sensitive to water concentration. Yeah, I told you before, because of its attenuation, and therefore water absorption is evident in the terahertz properties measured from the soft tissues, and which explains the contrast seen between the muscles and the adipose tissue. Consequently, terahertz rays images can distinguish between can basically distinguish between the healthy tissues and the basal cell carcinoma, and therefore help in mapping the exact margins of the early stage tumor. Which is like, this line is really very important when I say help in mapping the exact margins of the early stage tumors. So these early stage tumors, or defects in the tissues or any kind of things, can be detected by the terahertz images. So that is why it's like most promising are, like, for example, these non-invasive terahertz imaging technique we can use, like terahertz pulse imaging, terahertz time domain spectroscopy, and other generation detection methods. Okay, moving to the another slide. Again, you can see the image of imaging of tissues, biopsy, basically, where we can have the terahertz spectroscopy. So by obtaining both like frequency and time domain information of the tissues, terahertz image can ensure enhanced detection of cancer and other areas, and provide sharper imaging and molecular fingerprinting, because it has like high resolution imaging. uh, each year, millions of biopsies of breast tissues are required to compensate for uncertain, inaccurate, or negligent diagnosis delivered by means of conventional detection methods, and that they are not always impeccable. So apart from many other methods of diagnosis which are done uh, to do the biopsies of like the breast tissues, basically. So the thing is that conventional detection methods are not always like impeccable. So the terahertz time domain spectroscopy can reach the shortcomings of other medical diagnostics in rendering adequate images of affected tissues or suspected areas. Many researchers confirm that in a certain frequency range, most tumors have lower absorption than normal tissues. So the obvious conclusion here is that terahertz imaging can really and easily distinguish tumors from normal tissues. In addition to help in save human lives, such biopsies enhanced by T-ray spectroscopy save a lot of time and effort. This is also another important time, that this kind of spectroscopy technique saves a lot of time and effort by reducing the number of repeat surgical procedure in breast and skin cancer treatment issues. So you guys already knowing about that if a patient or if a person get diagnosed with a cancer, if it's in the second stage or something or third stage. So there are other methods which are done to basically kill or reduce that part of the affected tissues, uh, which basically the methods used are very harmful actually, and they can also affect the normal tissues also. So in that respect, if in the earlier stages of, like for example in cancer, if the earlier stages you can able to figure it out whether how what's the stage and how much the damage is, the treatment can be start at the initial stage. So this slide basically again showing the in vivo examination of tissues by spectroscopy imaging. So if you see in the image that there is in this box, a certain part is like really damaged, otherwise the other parts are of the tissues or the cell or the skin is fine. So in the imaging, you can easily figure it out. Okay, what's the problematic area or what's the inflammatory area. So you can have a, like targeted areas where you can reduce it by using lasers or something. So during this surgeries, the tumor is like often excised with an ample margin of surrounding healthy tissue. So the surroundings, it has the healthy tissues, and there might be a tumor in the center. So, such applying its safe approach in surgery is often justified, but costs dearly to patients and setback to the regeneration or recovery period significantly, because in that case actually you might damage the healthy tissues also. So imaging in the terahertz frequency range can be used to render real-time imaging during surgical operations to avoid cutting off a lot of healthy tissue and just leaving the part of that tumor in the patient body, or just taking out that part. So this in turn considerably reduces the likelihood of the need for the repeat invasive operative intervention in the future. So definitely by using the terahertz technology, you can cut it out the cost and the time, and really it can help in the medical field. Okay, now we have moved to the another application of terahertz, which is like terahertz imaging for sciences. So now I'm moving towards a bit more like technical part of the applications, where you can see in the terror spectroscopy, you have like I mean it's very visible and easily you can see aspirin, and aspirin tablets and everything. So if you have like different kind of drugs or medicines, and you want to figure it out the absorption factors of different drugs or something, so this can also be done by using terahertz spectroscopy. And apart from that, apart from the medicines and everything, because they have like distinguished features or signatures in the terahertz frequency range, as you can see, they have like this different absorption factors at the different terahertz frequencies. The explosive materials, like RDX and other things, can basically you can figure it out because the explosive material may uniquely absorb at like 1.15 terahertz and at 1.85 terahertz, like for example RDX and others. So it can be like used to detect explosive materials by using this fingerprint images. So because you know about these materials or the explosive material like RDX, that okay, they have these features at these frequencies, so you can figure it out. Okay, this explosive material is which material, and this is the which or whatever. So this is, again, has application in spectroscopy. Okay, another quite interesting application is, you can see this 500 rupees note, which I think is not in the market right now, not continue. So the terahertz image, this is the terahertz imaging of a currency note, and you can see this watermark is image is visible. I mean, maybe many of you have tried by looking at this 500 rupees note, and you can see the faint image of Mahatma Gandhi on that area which is pointed. So basically, by using the terahertz imaging of the currency note, you can also figure it out whether okay this real note is really real or fake. And yeah, and another, you can see this image of terahertz imaging of a leaf enclosed in a brown colored envelope. The thick black part basically shows the absorption due to the water, because terahertz images can absorb the water. So if you have a dry leaf, if you have a wet leaf, you can also figure it out. So by do the scanning. And apart from that, organic molecules exhibit strong absorption from gigahertz to terahertz because of their rotational vibrational transitions. This was the point which I sorry. This was the point which I mentioned when I was talking about why what makes terahertz unique. So because of the strong absorption in the terahertz frequencies through rotational and vibration transition, you can they can provide the fingerprint in the terahertz band of these frequencies. Another application of terahertz is like sub-millimeter astronomy, where so the terahertz technology application has substantially grown in astronomy science due to increased interest in terrestrial remote sensing, like at 100 gigahertz and 1 terahertz frequencies. So you can see this image of showing the beginning of a new star formation. Obtaining images of astrophysical sources and interpretation of observed terahertz light in the astrophysical sources. Terahertz detects cold metal like 140 Kelvin or less temperatures, and then such as clouds of gas, dust in our nearby galaxies. So new star beginning to form radiate heat, and they contract, and they are clearly seen in the terahertz range. So we have applications of terahertz in astrophysics also, basically. Another important application of terahertz is in communication. Uh, so, so basically, in the communication, as you can see in the image, I think it's the time of the need. Basically, that we are moving toward the faster, capabilities of faster data transmission in internet, which is like, I mean, the need of the day, where you can see the different basically pictures where you have these 5G cellular networks, you have the terabit wireless LAN, you have the terabit wireless personal networks in the military applications also. So so. So basically, if you see the annual global IP traffic passed the zettabyte limit at the end of 2016 and will reach 2 zettabytes per year by 2019. Moreover, peak hour internet traffic will reach 1.4 petabytes per second in 2019. Traffic from wireless and mobile devices will exceed traffic from like wired devices in 2017. So it's a time of like wireless things. So as the demand of for higher data rates increases, so does the need for the higher frequency brand that is able to transmit huge amounts of data to meet consumers' requests for the ever increasing data usage. So basically, in the mobile communications and other wireless communications, we are actually pushing towards higher data limits. So, and terahertz is like 10 to 12 hertz. So definitely the transmission will be like in the terahertz frequency, which are like quite higher. So this is another uh, application of terahertz basically in communication, which people actually are exploring, and scientists and many other companies are also collaborating to have these robust kind of means so that we can increase the data limit or transmission of data to a higher extent. Okay, so that was the end of the applications. I hope you guys not got bored, because there was lots of applications of error which you see, and I really mean it, because there are certain industries or companies which are working on these terahertz imaging systems and are providing cutting edge technology, like this terahertz cutting edge technology towards for the for the common people and others also. So, but apart from that, terahertz have some like quite a few shortcomings also. So this point, the first point I told you before, also the high water vapor absorption significantly weakens the terahertz wave signal during its propagation in air. So therefore, it is challenged to accomplish remote sensing with terahertz waves in air over several meters. So this is, a kind of a limitation where basically you can have because of the absorption of terahertz in water vapor, or because of the water vapors, these sensing kind of thing, and also in communication you can only have these terahertz radiations or application for like several meters, like few meters. Another thing is very few gases have no absorption lines in terahertz, for example, nitrogen. So that is why, like, mostly experiments which are done in the lab and also in the other platforms, they need or they use the nitrogen gas so that the absorption of terahertz basically reduces. So only like nitrogen is there, which can which have no absorption line terahertz. Apart from that, other gases or other things, the absorption of terahertz is high. The third point is that intensities generated are weak. For example, the terahertz energy still in like microjoules kind of thing. So people are actually trying to increase the energy of terahertz from microjoule to millijoule at least, which requires actually high power lasers and also different terahertz emitters. So these are also one of the things which people are working. And I myself actually have worked on various terahertz emitters, and I know the shortcomings of that, why we are not able to have terahertz energies from microjoule to millijoule. And currently, basically, I would like to actually say that in the current lab which I'm working in Hungary here, basically we are working towards to increase the terahertz energy from microjoule to millijoule by like various methods. So I think in the near future we'll definitely have terahertz with maybe like milliwatts, or not milliwatts, like the millijoule of energy. Okay, so finally we come to a conclusion for the end of this presentation. So I'll conclude my my presentation. So terahertz research will become one of the most promising research areas in the 21st century for transformational advances in imaging as well as in other interdisciplinary fields. However, terahertz imaging is still in its infancy compared to the relative well-developed science and technology at microwave, optical and X-ray frequency. Basic research, new initiatives, and advanced technology development in the terahertz bands are very limited and remain relatively unexplored. Much of the equipment used in terahertz research is large and heavy, and requires special operating conditions. I myself know that because I'm working in the lab because of this heavy, machines, and we require certain conditions to do the measurements, such as like controlled temperature and humidity, and use of liquefied gases. So, which makes it hard to implement these systems in real life applications. But actually, in certain applications, people have did a tremendous job to make it in a real life application. Research is underway to decrease the size and weight of the sources and detectors, as well as to make terahertz system less bulky, you know, tabletop kind of things, and easily to manipulate and demanding for the spatial operating condition. I think that's all from my side. Thank you very much for your patience.
Thank you, Abhishek sir.
Thank you,
And
members.
uh, we have some questions. So you come to the studio, and the question will be displayed at the video. So we
Uh,
have a question from Mohan HR sir. He's
mhm.
asking about the difference between millimeter waves and terahertz spectrum antenna.
What's the difference between millimeter waves and terahertz spectrum antenna? So actually, terahertz spectrum or terahertz waves are millimeter waves only. So as I mentioned in my, I think, which slide was slide number second or third. If you can scroll up, or maybe I can just try to. Just a moment. Yeah. So in the initial slide only, I showed you. Yeah. So you can, I think you can see that the wavelength range is like 3 millimeter to 30 micron basically. So terahertz basically is called a millimeter or a sub-millimeter wave. So I think what he's saying is what is the difference? I think the terahertz wave is like it's a millimeter wave only. Uh, so yeah,
Okay,
it's
sir.
a little
One another question from Narinder Singh.
okay. What kind of material generate terahertz? Basically, we can generate terahertz by using semiconductor. So there are like photoconductive antennas basically, which used gallium arsenide, semi-insulating gallium arsenide, and we also have alternative kind of structures on semi-insulating gallium arsenide. So we can generate like terahertz from semiconductors. We can generate from lithium niobate. So there are basically many materials from which we can generate terahertz. And but it depends actually. So basically, every material has certain limitations. So like for example, certain materials you can have like high terahertz range frequency in terms of frequency and energy, and some has low. For example, semiconductors, mostly like gallium arsenide, gallium phosphide are used, which like give like very low terahertz output. We make terahertz photoconductive antennas from that. So I think you moved the question. Sorry, can you again go back to the question? Uh, I actually read the first line only. Dr. Sembal, can you move to the previous question again? Yeah, sorry. So, so mean there is any kind of material task connected to yes, actually, organic and inorganic both. One is like dust, which are like quite high terahertz energy and frequency which are used. So yeah. So I think I answered it. Please move to the next question, please. Next question, please. Yeah. Can you
Yeah,
please?
yeah, sorry, sorry. This one.
Are terahertz harmful to those? Okay. When I was okay, I'll not say actually I'll not say like it's like 100% or maybe like for example the energies are in very less. The energy of terahertz is very low, and they do not the photon absorption is very low. It is not actually like harmful as compared to the X-rays and other. But if you have if you have a controlled kind of your terahertz radiation, and you want to have a detect on a particular point or particular part of your human body, if you have like focus kind of beam, and you have like all these parameters which where you won't give a threshold, above the threshold of the energy, it will not be harmful. But definitely, so actually, in this case, I will say it depends how you put up to the human body. But in normal and in general, it's not harmful.
So one another question from Sandeep Verma.
Uh-huh.
He's asking about the publications.
Okay, I have a few of publication in quite good journals. For example, I have publication in optics communication. I have publication in laser science and application. So okay, I think for more maybe discussing about publications or detail, you can have a look on my profile on the ResearchGate, where there are like all the publications are available, and if somebody finds interesting or want to read it, I can like personally send them the paper also which I have published. So basically, my earlier papers were mostly I published for the generation of the terahertz by using photoconductive antennas. So yeah, so for that, I think maybe you can have a look at my research paper.
So one another question. Uh,
So yeah, okay. Actually, this is a very good question from Mr. Chogyal. Terahertz waves technology, as far I know, are currently being used in the medical field, but not like on the very general scale, because there are things which you have to consider into the mind. But I'll say in right now in the current scenario in Europe or in the other parts of the continent, there are certain labs, or there are certain to say research kind of hospitals or the medical field where basically they are using terahertz frequency, but like not very common it is, but it is actually getting common day by day. But definitely about the terahertz scanners, I mean in Europe I see them in the thing.
This this one is another question.
Okay, can such waves can be generated using nanomaterials to enhance? Definitely, definitely. Actually, I have my papers on the terahertz metamaterial structure on the gallium arsenide semiconductor, where we have like enhanced output efficiency. So, Mr. Raninder Singh, if you want to like discuss further, maybe you can have a look on my research kit profile, where I have like certain papers where we have shown the increase in the output efficiency by using nanomaterial structures.
So one another question. This is regarding to your like personal lab and
Okay. Uh, Actually, there are research positions available, definitely, but for that you have to go to the LEL's website, and then in the section you can actually apply. And if your profile suits with our requirement, definitely we can.
so
Yeah.
one another question from Miss Radhika, Dr. Radhika. Sorry.
Can I take a 1 minute break?
Yeah,
Possible?
sure.
Yeah, just give me a minute. Huh?
Hello. Hello.
Yeah, sorry, I'm here again. What's the next question? Hello, hello.
Hello, yes, Abhishek sir.
Abhishek.
What's the next
Yeah,
question?
the question is on the screen: can these waves be generated using mechanical force or hydro force?
Sorry, yeah. Can these waves be generated using mechanical force or hydro force? Uh, okay. Actually, it's a very interesting question. The thing is, basically, uh, I remember one thing which we used to do when we were like measuring the terahertz energy by our terahertz emitters, like for example this gallium arsenide which I was saying, we used to check the terahertz signal just by waving our hand, by hand strongly. So basically, actually, the thing is, because we cannot see terahertz frequency, terahertz waves. So uh, there are many mechanisms or many ways where terahertz are generated. For example, like this mechanical force or hydro force, it can be generated. But the point is how you will actually record it or detect it. So this is a very important, thing to have proper detectors for terahertz, and also it requires, much more parameters to be involved. Just by normal mechanical force or hydro force, it's not possible. And even if you generate it, you cannot detect it. So if you have some like generation processes, you have to have some detection process also to detect them or to generate them. Yeah. Next question, please. Can X-ray technology be completely replaced by technology into medical field? I think yes. I think yes, but maybe not like currently completely. But as I was saying before, also that definitely terahertz at airport terahertz scanners are used now readily. I mean, normally they are used here, and in other technologies also. Like for example, if you want to have yeah, like for example for the tooth and which I have shown in my slides, basically these things can be checked by terahertz technology, definitely. But it actually it is advancing quite a lot slowly because there are many industries, there are many scientists which are working towards the compact terahertz system. Because in the last slides, during the shortcomings of the terahertz, or in the last conclusion slide, I told you that because the systems are actually a big system, they are not like very tabletop small systems currently. uh, so that you required a kind of a moderate setup to basically check these systems. So if the people are or scientists are trying to reduce the size of the system to a compact size where you can just use terahertz very efficiently. So I think it can, but I'm not sure when it will. Yeah. Thanks.
So, thank you, Mr. Abhishek Gupta.
I would like to show one video if you have some
Okay,
time.
okay, yeah. Yeah, there is a video. So you can, I will share your screen so you can see.
Yeah, just share. Can you see this VLC media player file which is open or no?
No, sir.
Okay, actually, I think I have to again share.
Uh,
Maybe.
you have to again share this. Yeah.
Yeah, I'll share again. Okay, share my screen. Share screen. I have to. Yeah. Okay. Now it's visible.
This is,
See?
yeah, yeah,
So
sir. Now
should I play?
visible. Yeah.
Should I play the video?
Yeah.
Okay. Okay. Here it goes. Huh?
Radio waves are long electromagnetic waves, and light and X-rays are short electromagnetic waves. Both are located on the electromagnetic spectrum. Electromagnetic waves already have many popular uses thanks to our ability to produce and control them. But while our current technology can create optical waves or radio waves easily, we lack the means to produce a very useful type of electromagnetic waves located right here between the radio and optical regimes. These are called terahertz waves. At the Laboratory for Nanoscale Electro-Optics, we are experts in the interaction between light and nanomaterials.
Abhishek sir, are you able to hear me?
Project funded by the European Research Council, we have engineered a family of sophisticated nanostructured metamaterials that are a mere few tens of nanometers thick, but are able to generate controlled terahertz waves. To activate the metamaterials, we shine ultra-short pulses of infrared light at them, and the waves that come out are the elusive terahertz waves. Importantly, the emerging waves also carry a certain functionality encoded in the metamaterial. Our development can be used, for example, to create devices that will allow to safely see through opaque materials and identify small structures and their composition, or to discriminate between real and fake medicine without even opening the box, and even for studies of art. By generating application-tailored terahertz waves, our metamaterials provide a promising new tool for terahertz science and applications.
Thank you. Thank you.
Thank you, Abhishek sir.
Yeah, thank you very much.
Thank you, sir. So all participants, please mark your attendance on the given link. And I hand over the mic to Mr. Diwakar Pant to conclude the session.
Thank you, Dr.
Mr.
Sunil
Pant?
Semwal, sir. Thank you very much, Dr. Sunil Semwal, sir. I would like to thank you, Mr. Abhishek Kumar Gupta, who has given time from his busy schedule. And I also like to thank all the participants and for their nice questions and answer session also. So once again, thank you very much to all and have a nice day.
Thank you, Diwakar Pant, sir. Okay, tomorrow we will have a session on communication for smart home automation and smart tech-enabled devices. The session will take by Mr. Naveen Kumar. He is the research engineer. So we will meet tomorrow at same time. Thank you very much. Thank you.